Now let's try to figure out an answer to our second question. It now becomes, for which values of x does the Taylor series of f at a converge to f of x? We know that if f has a power series expansion at a, that power series must coincide with the Taylor series. For any value of x, the Taylor series will sum to f of x only if the limit of the partial sums of the Taylor series converges to f of x. We let Tn of x be the partial sum of the Taylor series at x, which ends at the nth derivative at a over n factorial times x minus a to the n. So it's the sum of all terms of the Taylor series up to the x minus a to the nth term. And this is called the nth Taylor polynomial of f at a. And now the remainder, when I subtract that nth Taylor polynomial at x from f of x, is called Rn of x. And this is called the remainder of the Taylor series, or the nth remainder of the Taylor series. And with f of x, Tn of x, and Rn of x described as above, if the limit as n goes to infinity of Rn of x is 0, for all values of x between a minus r and a plus r for some r, then f is actually equal to the sum of its Taylor series. So this is just restating that the Taylor series converges to f of x at x if and only if the limit of the partial sums of the Taylor series is equal to f of x. In order to figure out whether the Taylor series converges to f of x at some point x, it's crucial to be able to figure out the limit as n goes to infinity of the remainders Rn of x for x values near a. And to help us do this, we have something called Taylor's inequality, which gives us an upper bound on the values of these remainders. So for any fixed n, and any x between, say, a minus d and a plus d, where d is some number, if the absolute value of the n plus 1th derivative at x is less than or equal to some fixed number m, then the remainder Rn of x of the Taylor series has the following property. Its absolute value is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. And this holds for all values of x between a minus d and a plus d. Now this is kind of complicated to digest, but let's see how it applies in an example. So what am I saying? Suppose I'm thinking about the Maclaurin series of f of x equals sine of x at, of course, a equals 0. The n plus 1th derivative of f at x here for any x is either plus or minus sine of x or plus or minus cosine of x. So the absolute value of the n plus 1th derivative at x, no matter what x is or no matter what n is always going to be less than or equal to 1. In Taylor's inequality, I can use the value 1 for capital M. And of course, because we're talking about the Maclaurin series, we can substitute a equals 0 for a in Taylor's inequality. And now what does Taylor's inequality say? So it says that for whatever d I might choose, in fact I can choose d equals infinity here, given any x between 0 minus d and 0 plus d, the absolute value of the nth remainder at x, that is the absolute value of sine x minus the value of the nth Taylor polynomial, the absolute value of that remainder is less than or equal to m over n plus 1 factorial times the absolute value of x to the n plus 1. And of course, we know that m is 1, so it's less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial. Let's see what Taylor's inequality says about e to the x. So if h of x is e to the x, and let's suppose I'm thinking about the Maclaurin series or the Taylor series around a equals 0, and I would like to get an upper bound for the absolute value of the n plus 1th derivative of h at x for all values of x in some interval 0 minus d to 0 plus d. I know that the n plus 1th derivative of this function is just going to be e to the x. So I would like an upper bound for the absolute value of e to the x between minus d and d. And of course e to the x is an increasing function, so e to the x is going to be less than e to the d for any x in the open interval from minus d to d. So in Taylor's inequality, capital M can take the value e to the d here for whatever value of d I might choose. And now Taylor's inequality applied to the Maclaurin series for e to the x says that the absolute value of the nth remainder is less than or equal to m over n plus 1 factorial times the absolute value of x to the n plus 1 for all values of x less than or equal to d. So in other words, the absolute value of e to the x minus the nth Taylor polynomial at x for this function h of x is less than or equal to this upper bound on the derivatives e to the d over n factorial times the absolute value of x to the n plus 1 whenever x is between minus d and d.